Today we are going to learn about mastering feature scaling for machine learning. This video will teach you how to effectively apply feature scaling techniques, focusing on improving model performance and ensuring algorithm convergence. Welcome to our video on mastering feature scaling for machine learning. Feature scaling is a crucial pre-processing step that transforms your data to fit within a specific range, enhancing the performance and convergence of machine learning algorithms. Whether you're working with SVMs, neural networks, or distance-based algorithms like KNN, understanding feature scaling is vital. Today, we will explore various scaling methods, discuss when to use them, and provide practical examples to solidify your understanding.
Feature scaling is the process of normalizing the range of independent variables or features of data. In other words, it's a method used to standardize the range of features of data. In the context of machine learning, it involves adjusting the scale of features so that they contribute equally to the result. This is particularly important for algorithms sensitive to feature magnitudes, such as support vector machines and k-nearest neighbors. By scaling the features, we ensure that the model learns effectively from the data without bias towards any particular feature scale. Common techniques include normalization and standardization, each with specific applications and benefits.
Normalization and standardization are two key techniques used for feature scaling. Normalization typically rescales the feature to a range of 0, 1, using min-max scaling. It's especially useful when you know the feature's minimum and maximum values or when you want to maintain the proportion of the data points. On the other hand, standardization rescales features to have a mean of 0 and a standard deviation of 1 using z-score scaling. This is beneficial when the data follows a Gaussian distribution or when you need features to have the same variance. Choosing between these methods depends on the specific algorithm and dataset characteristics.
Minute-max scaling, or normalization, is a straightforward method for scaling features to a range of 0, 1. It's particularly useful when you know that the data is bounded and you want to maintain the original distribution of the data points. This method is ideal for algorithms that don't assume any specific data distribution. However, it's sensitive to outliers, as they can significantly distort the scaled values. Therefore, it's crucial to handle outliers before applying min-max scaling. Despite its sensitivity, min-max scaling can be effectively used in scenarios where the feature range is known and consistent across different datasets. StandardScaler is a powerful tool for standardizing features by removing the mean and scaling to unit variance. Implementing StandardScaler in Python is straightforward, thanks to libraries like scikit-learn. First, import the StandardScaler from sklearn.preprocessing. Then, fit the scaler to your data using the fit method, and transform your dataset with the transform method. This process ensures that each feature is centered around 0 with a variance of 1, making it ideal for algorithms that assume a Gaussian distribution. During implementation, remember to fit the scaler only on the training data to avoid information leakage. Let's look at a practical example in Python to illustrate these steps.
Feature scaling plays a significant role in the performance and convergence of support vector machines, SVMs, and neural networks. SVMs rely on the distance between data points to find the optimal hyperplane, making them sensitive to feature scales. Without scaling, the model might give undue importance to features with larger ranges. Similarly, neural networks benefit from scaling as it helps in faster convergence by ensuring that gradients are not skewed in any particular direction. By standardizing or normalizing the data, we can enhance the speed and stability of training, leading to better model performance and generalization. Outliers can significantly affect the performance of scaling methods like min-max and StandardScaler. RobustScaler offers a solution by scaling features according to the interquartile range, making it less sensitive to outliers. It uses the median and the interquartile range for scaling, ensuring that extreme values don't skew the scaled data. Implementing RobustScaler in Python is simple and similar to other scalers. Import from sklearn.preprocessing, fit to the training data, and transform accordingly. By using RobustScaler, you can ensure that your models are robust to outliers, making it a valuable tool for datasets with significant outlier presence. Distance-based algorithms like k-nearest neighbors, KNN, rely heavily on the concept of distance to classify data points. Without proper feature scaling, features with larger ranges can disproportionately influence the distance calculations, skewing the results. By applying feature scaling, such as normalization or standardization, we ensure that each feature contributes equally to the distance computations. This results in a more balanced, accurate KNN model. We'll demonstrate the impact of scaling on KNN using a practical example, showcasing the difference in performance between scaled and unscaled data. By the end, you'll understand why feature scaling is indispensable for distance-based algorithms.
To solidify your understanding of feature scaling, let's dive into some practical examples using real-world datasets. We'll use Python and libraries like scikit-learn to demonstrate the implementation of different scaling methods, including min-max scaling, StandardScaler, and RobustScaler. By analyzing the performance of models before and after scaling, you'll see firsthand the impact on model accuracy and convergence. These examples will provide you with the skills needed to implement feature scaling in your own projects, ensuring that you can optimize your models for superior performance. In conclusion, mastering feature scaling is a vital skill for any machine learning practitioner. By understanding and applying techniques like normalization, standardization, and robust scaler, you can significantly enhance the performance and reliability of your models. Remember, the choice of scaling method depends on the specific algorithm and dataset characteristics. By incorporating feature scaling into your data preprocessing workflow, you ensure that your models are well prepared for training, leading to better results and outcomes. Thank you for joining us, and we encourage you to continue exploring and practicing these techniques in your machine learning projects.